In this lecture, we are going to discuss about certain curves of discontinuity associated to second order quasi-linear partial differential equations. So, we start with a brief review of the lecture 3.1 and then we move on to discuss curves of discontinuity. So, as you know, the second order quasi-linear equations we are denoting by 2QL and it stands for a uxx plus 2b uxy plus c uyy plus d equal to 0, where a, b, c, d are functions of this x, y, u, ux and uy. So, they are defined on some subset of R phi, which is called omega phi. And a special case would be a linear equation, second order linear equation. It has the general linear equation looks like this. So, let us start with a review of the previous lecture. We have considered the following Cauchy problem in the lecture 3.1. What is that? Find a solution to the second order quasi-linear equation satisfying u of fsgs equal to hs and the normal derivative of u at a point fsgs is chi s. What is fsgs? It is a curve parametrically given in a plane gamma 2 and the curve is a regular curve, that means f dash and g dash do not vanish simultaneously. So, along this curve we are specifying the value of u as h and the normal derivative of u as chi. So, these functions h chi are given. So, this is often called Cauchy data along gamma 2. So, we observed that the first order derivatives of u at points of gamma 2 can be computed using the Cauchy data. For that, what all was needed is that the curve gamma 2 is a regular curve, that was good enough. Then we also tried to compute second order partial derivatives of u again along the curve gamma 2. It can be computed using Cauchy data and now we have to involve the partial differential equation as well. So, the second order quasi-linear equation using these two we can solve, but one more condition was to be met. So, that was delta of s is not equal to 0. What is delta of s? It is this expression, okay, c f dash square minus 2b f dash g dash plus a g dash square. We know what f and g are, okay. These are the functions which describe the curve gamma 2 parametrically. Then what is zeta s? It is a 5 tuple which is fs, gs, hs, ps, qs. We have already solved for ps and qs, okay, using chi and h. Therefore, this makes sense and we can ask this condition. If this is non-zero, delta s not 0, then we can compute second order derivatives and we have also shown that higher order derivatives can also be computed. No further extra conditions are needed. Now, we would like to understand this condition in more detail. What is this curve? Okay, what is this? Where delta s is identically equal to 0, how that curve looks like. So, let us assume to start with that the gamma 2 that we considered is not parametrically defined, but let us say it is a graph of a function of the type x equal to phi y. Okay, it is a graph of a function of the variable y, x equal to phi y. Then what happens to gamma 2? X equal to fs, that will be phi s, y equal to gs which is s, okay. Y we parameterize as s, then x becomes phi s. So, this is a parametric representation and s belongs to that set where y belongs to. Wherever this function phi is given the domain, s belongs to the same domain. We are not writing that right now. Now, what will happen to this equation? Now, we need to substitute what is hs, ps and qs. hs is still general, ps and qs are to be determined from hs and chi s. So, these are still unknown, but what is known is f dash. F dash square is phi dash square, g dash is 1. So, this equation becomes this equation. Of course, if you want to know what function satisfy this condition, we need to still know this h, p and q. Okay, that is the problem with this equation, because the equation is quasi-linear equation. So, for a quasi-linear equation, if you are interested in this question, then you must be given a solution of the equation. Then you can ask what is that curve which will have this property. That can be now determined because solution is given, therefore, you know what is p and q. So, it makes sense. On the other hand, if the equation is actually linear, the ABCs are not functions of zeta s at all. Zeta s is a 5 tuple, they are simply functions of the first two variables fs and gs. And what is fs and gs? That is phi s and s. So, therefore, you know explicitly c, b and a only in terms of phi. So, it will be a differential equation for phi. So, it further reduces in the case of a second order linear equation to a simpler equation. For a quasi-linear equation, however, we need to be given a particular solution for which we can ask what are the curves x equal to phi y along which there is a problem in finding higher order derivatives. Problem in the sense we are unable to, our scheme of things fails, our scheme to compute the second order derivatives onwards fails because delta s is 0 there. So, as we saw, these are special to the PDE because the definition of course involves the equation. So, yeah, for the linear equation this gets simplified to this x equal to phi y. So, this is a differential equation nonlinear, first order, degree 2, nonlinear, and coefficients will involve only two variables now because we have linear equation. So, one can hope to solve this for phi. Then we would have got the curve x equal to phi y, where phi is a solution of this ODE, is a curve along which delta s is identically equal to 0, or there are troubles in solving for higher order derivatives. In other words, along these curves there is some problem to determine higher order derivatives of the solution or of a possible solution. So, even if you know solution, there is a problem to determine that because of delta s being 0. Now, the curves gamma 2 for which delta s identically equal to 0 holds are special to the PDE, as PDE also plays a role in their definition apart from gamma 2 itself. The same curves appear in a different context also. So, for piecewise smooth solutions of the second order quasi-linear equations, the curves of discontinuity, curves of discontinuity also satisfy delta s identically equal to 0. So, let us start, we are going to state a result. In the form of a result, it will be easier to remember. So, hypothesis and notations. Suppose you have an open and connected set in R2 and take a curve in R2 gamma that divides omega into two parts. So, that means that we have this, let us say this is omega, and we have a curve gamma which cuts this into two pieces, one is omega 1, other one is omega 2. So, what is omega now? Omega consists of omega 1, omega 2 and this curve gamma, the part of the curve gamma. We are going to assume that the curve gamma is given by x equal to phi y. We have already seen its interpretation in lecture 3.1. Why do we consider x equal to phi y? Once again we will give at the end of this result. So, given V1 in C of omega 1 bar, which means that you are given a function V1 here which is continuous on omega 1, of course omega 1 open set, but it should be continuous up to the boundary of omega 1. In other words, what actually we want is its meaning on this curve. So, therefore, V1 on the curve gamma makes sense. Similarly, V2 is in C of omega 2 bar means that the values of V2 on the curve gamma makes sense. It will guarantee that. Apart from of course, on this boundary also they make sense because it is continuous up to the closure of the domains, in this case omega 1, in this case omega 2. If such functions are given, we can look at the value of V2 on gamma and V1 on gamma, it makes sense, meaningful. Therefore, we can look at their difference. Let us see. Okay, let us define a function V. In omega 1 it is V1, in omega 2 it is V2. Let box of V denote the jump in the values of V across gamma. That means the definition is take a point xy on gamma, this is omega 1, this is where V1 is defined, this is where V2 is defined. We have seen V2 of xy makes sense when xy is in gamma. Let us call this part as a gamma, may not be the outside part. Okay. V2 of xy makes sense, V1 of xy makes sense because V1 is also continuous up to the boundary, in particular its values on gamma makes sense, and we can consider the difference. You could have even taken V1 minus V2, there is no problem, and we are considering V2 minus V1. So, this is called jump in the function V. That means, you have a function V defined on omega 1, here you have a function, here you have a function which is continuous, so that the values make sense along this curve gamma. Then you look at the jump in V as V2 minus V1 at points of gamma. Let ux and uy be continuous on omega, and the restrictions of u to omega I, they are C2 functions because we want them to be solutions to the PDE. So, that is why the C2ness, and we want omega I bar because we are going to consider the jumps in second order derivatives. First of all, derivatives should be meaningful on the curve gamma, okay, on this curve gamma. So, if I assume u is C2 of omega 1 bar, we may put 1 on the head, u1 is C2 of omega 1 bar, it means that second order derivatives of u are defined on gamma because they are continuous in omega 1 bar. That is the reason why we have this condition. So, let gamma be given by x equal to phi y, where phi is a C1 function. Now, the jumps in uxx, uxy and uyy are not independent of one another, okay. It means they are interrelated. To start with, it looks like yes, uxx is a jump in second order uxx derivative, this is jump in xy derivative, this is jump in yy derivative. Why should they be connected? So, let us denote lambda y as a jump in uxx at a point on gamma. A point on gamma looks like phi y comma y. So, then this is the result, jump in uxy is in terms of lambda y and phi dash, and jump in uyy is lambda into phi dash square. We are going to prove this. So, they are related. Observe that if lambda y is 0, what will happen? Lambda y is 0 means the right hand sides are 0 here, which means jump in uxy and uyy are zeros. That means if jump in uxx is 0, then jump in uxy as well as uyy are 0. Okay, let us prove the conclusion 1. The restrictions of a function defined on omega to the regions omega 1, omega 2 are denoted using superscripts. That is, we had this as the omega and we had a curve which is making it into two parts, omega 1 and omega 2, and suppose we have a function u defined on omega or any function u, ux, uy. We denote the restriction of u to omega 1 by u1 and here by u2. So, ui is u restricted to omega I. Since u, ux, uy are assumed to be continuous on omega, these functions are continuous across gamma also. In other words, there are no jumps across gamma. So, jump in u is u2 minus u1, phi y comma y is a point on the gamma. Similarly, the jump in ux defined by ux2 minus ux1, that is also 0. jump in uy is also 0. So, on differentiating the equations 2b and 2c, the last two equations, differentiate them, because differentiating the first equation will not give you anything, because if you differentiate this with respect to y, what will you get? Nothing useful, because we want to now consider jumps in second order derivatives, that is the reason. So, we differentiate the last two equations on the previous slide, we get this by differentiating the first equation and this by differentiating the second equation. Now, in terms of the jumps, this equation is nothing but jump in uxx into phi dash plus jump in uxy equal to 0, that is the first equation, and the second equation is jump in uxy, which is this, into phi dash and jump in uyy equal to 0. So, conclusion 1 of the theorem follows from the last two equations, because we called uxx jump as lambda, then jump in uxy is minus lambda phi dash. Therefore, jump in uxy is minus lambda phi dash, that will give you jump in uyy is minus lambda phi dash into phi dash. That is the conclusion 1. Let us look at the conclusion 2 of the theorem. For that we need to assume the hypotheses are u1 and u2 solve the quasi-linear equations in the regions omega 1 and omega 2 respectively. Let y be such that lambda y is not equal to 0. Recall, lambda is the jump in uxx at the point phi y comma y. Conclusion, denoting by zeta y equal to this quantity phi y comma y, u at the point phi y comma y, ux at the point phi y comma y, uy at the point phi y comma y. Recall, the point phi y comma y means x equal to phi y. This is how a point on gamma looks like. So, the following equation holds, we are going to show this equation holds. Whenever lambda y is not equal to 0, at that point this equation holds. So, if you assume lambda y is not equal to 0 at all the points, then the equation holds for all y. Then this equation is same as delta s identically equal to 0. Proof is very simple. We are going to assume that u1 and u2 are solutions, therefore, we can write down these equations in omega 1 and omega 2 with appropriate superscripts. So, we have this. Now, we have two equations, we have to subtract one from the other, and we have assumed that there are no jumps in ui, u, ux and ui. Therefore, the coefficients a, b, c, d, they all are like this, they are functions of x, y, u, ux, ui, there is no jump in them. So, this a will come out to be a. So, only you pick up the jump in uxx. So, 2b will remain as it is, because the it is a continuous function and it is the same in both. Therefore, along gamma, what I mean by same in both is this. Okay. You have an expression for, let us say here a is x, y, u1 of course of x, y, ux 1 x, y, ux uy 1 x, y. We have this, and here what we have is exactly same, but with 2. Okay. Now, on this curve, if xy is here, then both are same, because there is no jump. ux2 is same as ux1 when xy is on this curve gamma. That is why when you subtract, they come out as they are, and the d term gets cancelled, because the same in both of them when you are looking at points of gamma. So, you pick up only the jumps in uxx, jump in uxy, jump in uyy, they come here. So, we have this. So, using the conclusion 1 of theorem in the last equation, we get 0 equal to a of zeta y lambda y minus 2 b of zeta y lambda y phi dash plus c of zeta y lambda y phi dash y square. So, if you take lambda y common, what you get is this, a minus 2b phi dash plus c phi dash square, Assuming that lambda y is not equal to 0 along gamma, we get this, the one in the brackets must be 0. If lambda y is not equal to 0 for all y, then this, the one in the parenthesis must be 0. So, we get this differential equation, and this equation is the same as delta s equal to 0 for s in I, same equation when x equal to 5i. So, we have assumed that the curve is of the form x equal to 5i. The conclusion 3 of the theorem is as follows. Hypothesis: assume u1 and u2 solve the linear equation in the regions omega 1 and omega 2 respectively, the linear equation, and u possesses third order partial derivatives that is required for stating this conclusion, and have jump discontinuities across gamma. Let y be such that lambda y is not equal to 0, then lambda satisfies the following ODE: 0 equal to 2 into b minus c phi dash into lambda dash plus this quantity into lambda. So, this is a linear ODE with variable coefficients because they depend on y, this depends on y. So, it is a linear ODE with variable coefficients. Of course, if b minus c phi dash equal to 0, then this will be a singular ODE, otherwise it is a linear ODE. Okay. Now, observe that if b minus c phi dash is not equal to 0 and a, b, c, phi are smooth functions, then lambda y equal to 0 at isolated points implies that lambda y is identically equal to 0. Let us understand this carefully. If lambda y is equal to 0 at some point, this ODE may not hold, but we are here the hypothesis lambda y equal to 0 at isolated points. That means the points where lambda y equal to 0 can be reached by the points where lambda y is not equal to 0, at which the ODE holds. This ODE makes sense because whenever lambda is not 0 at some point, the ODE happens, the lambda satisfies this ODE. And you see, this is a equality, as people say, the equality is a closed condition. Therefore, it follows that even if lambda y equal to 0 at isolated points, this ODE continues to hold. Okay. And if you are assuming all these functions are smooth and this is non-zero, then it turns out that the quantity in these brackets and the quantity in these brackets are smooth functions and they are locally Lipschitz functions. Then we can apply uniqueness theorems for the initial value problems and conclude that lambda y is identically equal to 0. So, lambda y by definition is jump in uxx, which is this. Differentiate both sides of this equation, you get lambda dash with respect to y, therefore, you differentiate this with respect to x, you get u triple x, but phi is there, therefore, phi dash, and from here you get u triple x into phi dash. Now, differentiate uxx with respect to y variable, you get this, similarly this you get this. Therefore, we can express d lambda by dy as jump in u triple x into phi dash plus jump in u xxy. Now, similarly, we can also get derivative of uxy. You write the equation for uxy jump, differentiate with respect to y, you will end up with this relation. Now, we know that uxy jump is minus lambda times phi dash, that is a conclusion 1. Therefore, this equation I can write it as this. Now, we are going to use ui solve the linear equation in the domain omega I. So, we have this two equations, one in omega 1, one in omega 2. Along gamma we will consider because we are going to take jumps. So, first is to differentiate this with respect to x because we are interested in third order derivatives, differentiate with respect to x, then subtract one from another, we get this expression. Now, once again use the conclusion 1 of the theorem, which expressed basically the relations of jump in uxx, uxy and uyy in terms of lambda, which is actually jump in uxx. So, we get this relation. So, we have 3 equations, this and the one we just obtained, this. Now eliminating the jumps in the third order derivatives of u across gamma and using this relation that a minus 2b phi dash plus c phi dash square is 0, that is the equation phi has to satisfy, right, even for quasi-linear equation, therefore for linear equation also. So this equation is satisfied. So how do we eliminate? That is what you have to look at. So we want to remove these conditions. We have 3 relations in them, maybe solve for them, that is what it is, and substitute, and we get the ODE in conclusion 3. So this is left as exercise to you. This is a simple algebraic exercise. Now we may interpret this lambda as the intensity of the jump in uxx, intensity of the jump in uxx across gamma. This interpretation is taken from the book of Fridjohn on PDEs. So if lambda y naught is 0 for some y naught, that is lambda is 0 at some point, and if the initial value problem that we had for the ODE has a unique solution. What is the ODE that we were considering? It is that linear equation for lambda which we saw, 2 into b minus c phi dash into lambda dash plus a huge expression into lambda. Okay. If that has a unique solution, of course it is a homogeneous linear equation, 0 is always a solution, and if it has uniqueness also, then it must be that lambda is identically equal to 0. We already did this conclusion. So if uxx is continuous at some point, this is the interpretation in terms of uxx. What is lambda after all? It is a jump in uxx. If jump is 0 means what? Ux is continuous at that point, then it is continuous at all points of gamma. And therefore, once you have uxx jump is 0, jump in uxy and uyy is also 0 from conclusion 1. So location and speed of jumps. If the variable y is given the interpretation of time, the equation x equal to phi y gives the location of the jump in uxs for various time instances at different instances of time. The speed of propagation of discontinuities is given by dx by dy, which is equal to phi dash of y. Dx by dy is phi dash of y and satisfies the differential equation a of zeta y minus 2b zeta y phi dash plus c of zeta y phi dash square, where zeta y is given by this phi tuple. So let us summarize this equation, which is the ODE which is there on the slide. It appeared in 2 different contexts. In lecture 3.1, how it appeared? If the Cauchy data is prescribed along the curve gamma 2 x equal to phi y, where phi does not satisfy the above ODE, derivatives of all orders for a solution to 2QL can be determined at all points of gamma 2. In this lecture, if gamma given by x equal to phi y is a curve of discontinuity for second order partial derivatives for a piecewise smooth solution of 2QL, as in the theorem that we have stated today in this lecture, then phi solves the above ODE. Important question is, for a second order quasi-linear equation, how useful is this equation? Since to write down this equation zeta of y, it requires the knowledge of a solution to the 2QL, that needs to be given, right. So how is it helpful in identifying these curves x equal to phi y, where phi solves this equation? Once the function is known, can't we find curves of discontinuity directly? Do we still need to solve this ODE? Answers: if a solution is given, then in principle possible curves gamma across which second order derivatives may have jump are already known. Okay. However, the ODE gives an analytic characterization of such curves and thus may still be useful. Of course, for semilinear equations, the ODE is useful in both the contexts. Determine curves along which a Taylor series for a solution may be obtained, or identifying curves across which piecewise smooth solutions will have discontinuities in the second order derivatives. So, in forthcoming lectures, the ODE will play an important role in reducing a linear second order PDE to a simpler form. In the simpler form, the coefficients of second order derivatives will be constants. Okay, to start with, in a second order linear equation, coefficients are functions of x and y, but this ODE will help us in obtaining a simpler form of these equations in which the coefficients of the second order derivatives are constants. The simpler form would be obtained using change of coordinates. The ODE plays an important role in determining the change of coordinates. Thank you.